Okay, so in this segment we're going to convert something a little bit more complicated that's going to require a little bit more gadgetry going on with it. Not a huge amount, but just a bit extra. This is my JYE Tech pocket oscilloscope, which is a handy little, well, it's literally a handheld oscilloscope. You can see from the side of my hand here, it fits in the palm of your hand. And this thing is really handy just for quickly looking for digital signals on things, or even analog signals as well. It's just a handy tiny little oscilloscope. It's not terribly accurate, but it does the job. It runs on a 9-volt supply that I'm feeding into the bottom of it here from a DC power supply. Now, because it's 9 volts, you could also just run it on like a 9-volt cell, but it tends to drink through these, and I don't like 9-volt batteries because they're annoying and they're expensive, and just, nah, I'm not a fan of them. So this thing is kind of inconvenient to use most of the time because I've got to turn on my DC power supply and plug it all in. And if I'm using my power supply for something else, then obviously it's even more inconvenient to run this at the same time. So I really want to make this thing battery powered. So what we need to do for this is, like with the previous ones, we firstly need to identify how important its power supply is. So I already know from previous experience that when this thing is not receiving enough power, the signal that, there we go, I'm just going onto its test signal, the signal will drift on it. So at the moment we've got a nice Vmax of 3.4 to 3.44, and as you can see we've got a nice clean square wave going on there, or as clean as this thing gets anyway. So what we're going to do is I'm going to lower the voltage, and I'll just show you what happens when this thing drifts and why we need to make sure that we give it a steady power supply. So now I'm just going to start winding the voltage down. Right, and now I've dropped the input down to 7.4, which would be a 2-cell LiPo battery. And as you can see, the Vmax has dropped to 3.36 to 3.4. So we can already see that we've compromised the accuracy of this thing. And I also know from personal experience that when the battery starts to fade on this thing, you just start getting misleading results and just everything goes squicky and slightly out. However, it is reasonably tolerant. At 7.4 volts, you know, the screen is actually working fine and stuff like that. But because the accuracy is compromised, as a measurement device, it's immediately no good. So we can't just run this thing on raw battery voltage. And because it is not 5 volts, it's 9 volts, we also can't just run it off of a power bank board like we did with the scales. So we actually need to create our own 9-volt supply for this. So let me show you how I'm going to do that. So in order to get our 9 volts, we're going to use a bigger version of what we see on a USB power bank board. This is a DC-DC boost converter. And what this does is it boosts one DC voltage up to another. So we've got voltage in on this side and voltage out on this side. And how this thing works is it uses the standard DC-DC boost configuration. And that revolves around this inductor here. So this guy here, this is an inductor, which is a coil of wire around a ferrite core. It's basically an electromagnet to all intent and purpose. However, it just doesn't make a very intense magnetic field. Nothing that you could pick up something with, you know. And what will happen is when power flows through this inductor, that power will get converted into an electromagnetic field. So because some of it is getting converted into the electromagnetic field, this will resist the change in power going through it. So initially when the power starts rising, this will resist that change and convert that resistance into electromagnetic energy. And then when the power goes down again, it will resist that change once again, and in order to keep outputting while the input has gone low, the electromagnetic field will then collapse and go out as power. So you can think of it like a small buffer or a reservoir of energy that builds up and then goes out again. And so what will happen is this little controller chip here, what this will do is it will short the output of this to ground. So suddenly there's a massive inrush of energy from the voltage input and the power on this thing will suddenly go whoosh, and it will skyrocket. And then just as it peaks, this will turn off the short to ground, and then all the power in here will then need to go somewhere. So it will rush out through the output as a higher voltage. And what this will do is it will switch that on and off very quickly. It will switch this on and off at very high speed, so you get constant spikes of higher voltage going through the output. And then you have some filter capacitors that then smooth that out into a nice steady higher voltage. And then using this trimmer pot here, we can adjust what that voltage is set to. So let's take a look at it in action. Okay, so here's a demo setup of the board in action. I've set it to 9 volts, so let's just show you the input voltage here. So here's a LiPo cell connected to the input at 3.7 volts. Then the boost circuit is boosting that up to 9 volts on our output. So we now have a 3.7 volt LiPo cell outputting us a regulated 9 volts. So even as the cell voltage drops, as the cell depletes, this will continue to step that up to 9 volts right up until the voltage is too low for this thing to actually operate. And I'm not sure what the dropout voltage is. It's going to be pretty low. It's going to be significantly lower than how low we will allow our cell to go. So that's not really a concern to me. Okay, so this is a LiPo charge board that is very similar to the one that I used in the coin block that in a previous video. And we've got 5 volt input on the left here. And we've got the connections for a LiPo cell on the right. And these circuits here handle the charging. So these will regulate the voltage and the current to ensure that the LiPo cell is charged correctly. And then obviously, because it's a 5 volt input, you've got to do some step down voltage there as well. And we've got a couple of LEDs that indicate charge or charging status and so on and so forth. So this would be good for a single cell setup. Now, initially, when I was going to start working on the pocket oscilloscope, because it was running at 9 volts, I had considered using a 2-cell setup, because obviously a 2-cell battery would give me 7.4 volts at the start, and that's obviously much closer to 9 volts than 3.7 is. And however, if I had 7.4 volts and 2 cells, I would need a different kind of charging circuit to handle that, because my 2 cells would be in series. So the 4.2 volt charge voltage of this one here wouldn't work. So if I was doing that, I would use a board like this instead. So again, this is a LiPo charge control board. Now the interesting thing about this one is that it can handle a 2-cell battery. And this is handled by this little set jumper down here. If you bridge those 2 connections together with a blob of solder, it will set this board into 2-cell mode, where it will then assume that the battery voltage is 7.4 volts. And on the other side of it here, you can see that we have a 5 to 15 volt input range. Now, obviously, if we have 5 volts coming into this thing, our battery charge voltage at 7.4 is higher than the input. So you'll notice we actually have a big coil here. Look familiar? Yeah, that's right. This has got a DC-DC boost circuit built into it as well. So if you're giving it 5 volts of input, it can step that 5 volts up to 7.4 to charge 2 cells in series. So this is quite an interesting little widget. However, because of space restrictions, I'm only going to use a single cell in my pocket oscilloscope. Now you might ask yourself, well, why does anyone bother using multiple cell batteries if you can just step the voltage up anyway? Well, the answer to that is current handling. If I have stepped 3.7 volts up to 9 volts, I'm also changing the amperage, because you cannot get more volts without lowering the amps. So if I step the voltage up coming through this DC boost converter, the amperage at the output will conversely go down. Now, in order to compensate for that, the entire system will just simply pull more out of the battery. Okay, so how do we figure out if that's actually going to be a problem or not? Well, firstly, we need to know how much we're going to draw in total. Now, I already know in advance that The pocket oscilloscope draws 100 milliamps, and I know that because that is what my DC power supply shows when I'm using it. When I've got this thing plugged in and turned on, it's drawing 9 volts and 100 milliamps. So if you don't know the power rating of your widget, you're going to need to figure that out in advance, and I'm not going to cover that right now because that's just starting to drift off topic. However, we know we've got a 100 milliamp load here at 9 volts. So if we're pulling 9 volts and 100 milliamps out of our DC boost converter, how do we figure out what load that's actually putting on our cell? Because we don't want to overload the cell. So we can actually figure this out quite easily. Because we know the power ratings of this, we can calculate the wattage. So to calculate the wattage, we do volts times amps. So what I will do is I'll take 9 volts times 0.1 amps, because 100 milliamps is 0.1 of an amp. And that gives me 0.9 watts. Okay, so far so good. So now I know the wattage, we can now change the voltage. So what I do for that is I take the wattage and I divide that by the nominal voltage that I'm looking for, which will be 3.7. And that gives me 0.243. So we've got 100 milliamps, 9 volts at the output, and then at the input we're going to be pulling 3.7 volts nominal at 243 milliamps. So you can see that the cost of boosting the voltage up to 9 volts was we're more than doubling the load. We've gone from 100 milliamps to 243 milliamps. So we've significantly increased the load on the cell. However, this isn't a problem, because if we're running, I'm going to be running this thing on a 2 amp hour LiPo cell. And a 2 amp hour LiPo cell, generally speaking, a LiPo cell is usually good for at least 1 C of load. So that means 1 times the capacity of constant current. So a 2 amp hour LiPo cell is going to be more than happy with 2 amps. Now, you don't want to draw that all the time, but it can do it. So in this case, we're sitting at 0.24 amps. So we're well within the spec of our battery. Even if we assume that we've got the 18650s, they usually tell you that their nominal current is 1 amp. But even if we only had 1 amp nominal current, we're still only a quarter of the maximum load we can put onto our cell. It might drain our cell a little bit faster, but again, I'm not too worried about battery life on this project. Cool, okay, so we're absolutely fine. Okay, so, however, it's worth considering that if we had a bigger load, let's say that this thing was actually running at 1 amp instead, we had a 1 amp load on this because we were running a big torch or something like that. Let's just quickly run the numbers for that, just to demonstrate how that would turn into an issue. So let's run all of those calculations again. So we've got 9 volts times 1 amp equals 9. So we would have 9 watts. So 9 divided by 3.7. Now that would suddenly turn into 2.43 amps on the battery. So if we had a 1 amp load at 9 volts, 1 amps, you say, oh, that's fine, that's only 1 amps. We can pull that out of a LiPo cell. Yeah, not at 9 volts. If you've boosted your voltage up to 9 volts, you're actually pulling nearly 2.5 amps out of your LiPo cell. And that is going to cause a problem with a normal cell. But because we've only got a 100 milliamp load, we're perfectly fine with just a single cell and a DC-DC boost converter. Cool. This also means that I can use just a single cell charger circuit. So here's a 2 amp hour LiPo cell. Here's a DC-DC boost converter to get this thing up to 9 volts. And here is a little charger board to charge it with. Let's wire it all up and do a demonstration of it all in action. Also, pro tip, when you're using little eBay modules like this, check and double check the polarity of everything, because these little widgets that you buy, they very rarely have reverse voltage protection on them. So I'm just double checking the polarity of everything just so I don't accidentally wire it incorrectly. Right, there we go. Please excuse these rough as guts solder connections. We'll do all of this nicely when it goes into the device, but this is just a test setup. This fly lead will be coming off again anyway, so there's no point in me making it absolutely perfect. Cool, let's hook all this up and show it off in action. So, here we go. Power into the bottom of the oscilloscope. Let's connect a LiPo cell up to our battery connector, which is there. And turn it on. Right, and there we go. So now we have the oscilloscope running directly off of our setup here. So let's probe some of these voltages just so you guys can see what's happening here. So at our output, so there's our 9-volt output from the system that goes to the oscilloscope. And there is our we've dropped to 3.56 there, where we've actually got a load on the cell now. So there's the 3.5 volts, which will be slowly going down as the cell depletes, but the boost converter will continue to boost that up to 9 volts as it sags. And then over here on the input, we still have the same 3.5 cell voltage. Now comes the fun part. What I'll do now is I'll grab a USB charger and we'll plug it in to charge. And we can do this while it's still turned on, because the boost converter will just receive a higher input and it will lower its output to match. Right, now we're in charge mode. We've got a red light on our charge board, and if I probe the voltages again, what do you think is going to happen? We still have 9 volts on our output. However, but the cell voltage is now at 4 volts. And that will be slowly climbing as the cell charges. And if we just hold down here, you can see that we're actually very, very slowly climbing because the cell is now on charge. And even as that voltage climbs, we'll continue to boost to just 9 volts. And eventually, the cell will be fully charged, and this thing will automatically switch into a charged status, and the light will probably turn blue or something like that to indicate that we're now charged up. So that's our entire system. We now have a LiPo cell boosting to the nominal voltage we need for our device with a built-in charger system. Now all we have to do is put all of this into the case. Right, let's open this thing up so we can see where we're going to place everything inside it. It's going to be a little bit tight in there. However, I believe when I did my initial looks, there was room to fit it all in. There might be a little bit of ghetto modding, but it's not like you haven't seen me doing that in this stream already. So, okay, that opens up. Something opens up. Hello? There we go. Okay, so this thing is has 2 major parts, which I'm just pulling apart now. There we go. So we've got the analog board and the digital board. And if we place those sort of there-ish, as you can see, we've actually got a reasonable amount of space in here. This bit sticks down a fair bit. However, my plan is to put that about there. Okay. And if I'm just a little bit generous with the nudging, I think that will go about. I can just about fit in there and still allow the digital board to sit on top of the connector. And I believe that also clears this. I just put those together. No, not quite. Oh no, that's about flat. That's all right. That's more or less sitting in place. So, with that in mind, we basically need to fit our DC boost and charge board here. So let's see if we can do that. I'm going to desolder all the wires off of those, and we're going to get things stuck down in place and then solder wires between them. So let's turn the soldering iron back on. Okay, that's all the boards desoldered. So I'm going to want my cell there. The boost circuit can go basically anywhere and is going to connect into these jumpers on the back of the digital board. So in a perfect world, we might want to we may want to stick a JST connector on this. I might also remove the 9-volt input jack, because that will give me a little bit of extra space in the bottom left there. And then I might get a little bit cheeky and just trim out. If I trim out the corner of the case here, then I'll be able to fit the charge board down there and have the USB micro port sticking out the bottom. That'd be good. We lose this screw point, but I'm sure this thing will hold together with 3 screws in it instead of 4. I think we need to put some fly leads onto this. So I'm going to put some longer wires on it. Now I'm just going to tin up these jumper wires I've soldered, and then I can attach them to the cell and get that all taped up. And I'm just going to put that bit of Captain tape over my positive lead while I'm working on it so I don't accidentally short the battery against anything. Okay, right, that's ready. So that's going to go there. I think I'm going to remove the 9-volt jack to free up that area. Is that through hole? No, it's surface mount. Okay, let's try and take that off the board. Whoops. Oh, that one's not connected anyway. Okay, right, so we freed up some space in the corner of the board. So now this area is also free. So now we need to get this mounted up somewhere. So I think what we'll do is we'll get our jumper leads on the voltage out and get that going onto the DC board. And in fact, I may be able to mount that directly on the back of the DC board, because the positioning of this is much less important. So if I was a bit clever, I might be able to just plumb that straight in there, just to insulate both sides of the boards. That could work. Okay, right, let's just remove this bit a sec. Right, I'm going to be a little bit sneaky for this bit. I need some nice flexible wire to make these turns. So I've got some nice silicon wire here, which is being used in another project, but I'm sure I won't mind if I rob just a little bit. Silicon wire is handy because it makes nice tight turns and squidges easily. Okay, now just use a bit of double-sided tape to stick this guy down. Put that on top of those spiky bits that are sticking up. There we go. One boost board fitted to the back of the digital board, insulated in between and wired into the inputs. Good. I'm just going to clean that up. I left a load of flux residue on that. Cool. Looking sweet. So, let's do a quick fitment test just to make sure that we're not massively fouling anything up. Because I have placed that board exactly where my cell is going to go. So let's just find out whether that is actually going to fit or not, because I don't know, to be honest. Oof. It is tight, but it's in, and we've still got all of this space on the other side for the charge board. That would work. I kind of wanted it at the bottom, really, because then it can go through this part of the casing, which is already ruined. Just going to use a small bit of double-sided tape so it's held in place, but it's not like perma down. And then all we have to do is get the battery onto the back of it and 2 leads from the DC board round to there, which is not a huge task. Okay, fitment test. Yeah, we're bending everything a little bit. Is it going to work though? Woo lad, it will go in. And we've managed to retain all the screw holes as well. Right, I'm just putting some tactical curves in the cell wires, so they're just going to vaguely where I want them to. Okay, so, and I'm just going to trim the end of that, just so that's a bit less leery. And then we need another 2 jumper leads going back to our digital board. I think I'm going to be a bit cheeky and use some more of my nice silicon wire for that. I'm going to be gutted if I run out of this for the other project. We've got, we've got loads of it. Bloody hell. Ah, spaghetti! Spaghetti everywhere. Okay, here we go, crunch time. Now everything's got to go in. Okay, there we go. Power test. Okay, it starts. And charge test. And we're charging. Good, okay. Right, now do I need to put some more... Yeah, I'm going to put some more double-sided tape under that. Now I know I've got the positioning right. Okay, there we go. I've just squeezed it all in, and on goes the top. Oh, it's all a really tight squeeze, but it's going in. I'm going to put in some screws. That fitting is a bit tighter than I'd hoped for, but I think we're okay, to be honest. I think I can get away with that. Alright, here we go. Please don't blow up. Battery powered pocket scope. Dunzo. Let's check that it still works and that it's still accurate. Right, and there is our test signal. Sitting at 3.4 to 3.44 volts, which is what it was when we started off. And that's it. So yeah, I now have a battery powered oscilloscope with USB micro charging. I wonder if I can see, can we see the, where's my thing? I wonder if we can see the charge light at all. Well, there's a red glow in there. Yep. I mean, because I've got a hole where the barrel jack used to be, we've got a red light there, so I can see when it's charging as well. That's baller. That feels really weird, seeing this thing turned on without any power going into it. Huh. Good. I'm happy. Neato. Oh, there's one more thing that I missed from this setup that I forgot to mention. I used an unprotected lithium cell in this thing. So the eagle-eye people here may have been screaming at the screen for the past 20 minutes saying, there's no cell protection in this. You are absolutely correct. I have not installed any cell protection at all. There's nothing in this setup preventing me from over-discharging that LiPo cell. So I actually have to watch out for that. I don't actually have any means of measuring the current charge of the LiPo cell in this thing. So it's up to me to keep an eye on it. I can use the internal self-test to know whether it's drifting or not. And if the cell, well, you know what I really should have done? I should have figured out what the dropout voltage was on the boost circuit. Let's quickly do that now. Okay, so here's another boost regulator I've got wired up. So I've currently got this hooked up to the bench power supply and we've got it set to 9 volts. So we're outputting 9 volts. Let's start turning down the input voltage and see where it drops out. So this is 3.2. Okay, it's about 1.7, 1.8 volts. There we go, I've just got it right on the edge. Between 1.8 and 1.7 volts is where the dropout is, which is well below what we want the minimum charge of our LiPo cell to be. However, it's also worth noting that we have unlimited load. If we had the LiPo cell hooked up to this, when the cell voltage goes that low, the current is going to spike, which will tank the cell voltage even more. So we are at risk of over discharging the cell. However, I'll probably see the oscilloscope will probably drop out before we actually damage anything. So I'll probably get a little warning. And to be honest, again, it's a cheap recovered cell in there, so I don't particularly care. There's very little risk. The worst thing that I can do is kill the LiPo cell. So I'm not too fussed about that. But yeah, I am aware about it, and that's something that I will watch out for. I'll probably keep it charged all the time, to be honest, because I only use it in fits and starts. Right, well, that concludes that. So thank you very much for watching, everyone. That more or less concludes my How to Lipo mini-series. If you've got your questions, then smash them into the comments. There will have been something that I missed or got slightly wrong, I don't doubt in my mind. However, I hope that this little mini-series has been a rough crash course on how to effectively identify, use, and mess about with lithium cells. Remember, take care when you're messing around with these things. They can be dangerous, but only when you don't know what you're doing. So use your common sense, and yeah, that's it. Thank you very much for watching, everyone. I'll see you all next time. Goodbye for now.